The Internals of Postgres. Chapter 10, Base Backup and Point-in-Time Recovery. Online database backup can be roughly classified into two categories, logical and physical backups. While both of them have advantages and disadvantages, there's one disadvantage in logical backup, taking too much time for its performance. In particular, it requires a fairly long time to make the backup of a large database, and even more time to restore such a database from backup data. On the other hand, physical backup makes it possible to back up and restore large databases in a relatively short time, so that it is a very important and useful feature in practical systems. In Postgres, online physical full backup has been available since version 8.0, and a snapshot of a running whole database cluster, i.e. physical backup data, is known as a base backup. Point-in-time recovery, PITR, which has been available since version 8.0, is the feature to restore a database cluster to any point in time using a base backup and archive logs created by a continuous archiving feature. For example, even if you made a critical mistake, e.g. truncating all tables, this feature enables you to restore the database at the point just before the mistake you have made. In this chapter, the following topics are described: base backup, PITR, timeline ID, and timeline history file. In version 7.4 or earlier, Postgres had supported only logical backups, logical full and partial backups, and data exports. 10.1 Base backup. First of all, the standard procedure to make a base backup using the low-level commands is shown below. 1. Issue the pg start backup command. 2. Take a snapshot of the database cluster with the archiving command you want to use. And 3. Issue the pg stop backup command. This simple procedure is easy to use for database system administrators because it requires no special tools but common tools such as copy command or a similar archiving tool to create a base backup. In addition, in this procedure, no table logs are required and all users can issue queries without being affected by backup operation. Those are big advantages over the major open source relational database management systems. More simple way to make a base backup is to use the pg base backup utility, but it internally issues those low-level commands. As the pair of those commands is clearly one of the key points for understanding the PITR, we will explore them in the following subsections. Note: the pg start backup and pg stop backup commands are defined here. Source backend access transam xlogfuncs.c. 10.1.1 pg start backup. The pg start backup prepares for making a base backup. As discussed in section 9.8, recovery process starts from a redo point, so the pg start backup must do checkpoint to explicitly create a redo point at the start of making a base backup. Moreover, the checkpoint location of its checkpoint must be saved in a file other than pg control because regular checkpoint might be done a number of times during backup. Hence, the pg start backup performs the following 4 operations. 1. force into the full page write mode. 2. Switch to the current wall segment file, version 8.4 later. 3. Do checkpoint. And 4. Create a backup label file. This file, created in the top level of the base directory, contains essential information about base backup itself, such as the checkpoint location of this checkpoint. The third and fourth operations are the heart of this command. The first and second operations are performed to recover a database cluster more reliably. A backup label file contains the following 6 items, or 7 items in version 11 or later. We have checkpoint location. This is the LSN location where the checkpoint created by this command has been recorded. The start wall location. This is not used with PITR, but used with streaming replication. It is named start wall location because standby server in replication mode reads this value only once at initial startup. Backup method. This is the method used to make this base backup, either PG start backup or PG base backup. Backup from. This shows whether this backup is taken from primary or standby. Start time. This is the timestamp when the PG start backup has executed. Label. This is the label specified at the PG start backup. Start timeline. This is the timeline that the backup started. This is for a sanity check and has been introduced in version 11. Backup label. An actual example of backup label file in version 9.6 is shown in the following. Start wall location, checkpoint location, backup method, backup from, start time, and label. As you may imagine, when you recover a database using this base backup, Postgres takes the checkpoint location out of the backup label file to read the checkpoint record from the appropriate archive log, and then gets the redo point from its record and starts recovery process. 10.1.2 PG stop backup. The PG stop backup performs the following 5 operations to complete the backup. 1. Reset to non-full page mode. Reset to non-full page writes mode if it has been forcibly changed by the PG start backup. 2. Write a xlog record of backup end at backup end of backup end. 3. Switch the wall segment file. 4. Create a backup history file. This file contains the contents of the backup label file and the timestamp that the PG stop backup has been executed. 5. Delete the backup label file. The backup label file is required for recovery from the base backup, and once copied, it is not necessary in the original database cluster. Note: the naming method for backup history file is shown below. Wall segment dot offset value at the time of the base backup was started dot backup. 10.2 How point-in-time recovery works. Figure 10.2 shows the basic concept of PITR. Postgres in PITR mode replays the wall data of the archived logs on the base backup from the redo point created by the PG start backup up to the point you want to recover. In Postgres, the point to be recovered is referred to as a recovery target. Here's the description of how PITR works. Suppose that you made a mistake at 12:05 GMT of January 29th, 2019. You should remove the database cluster and restore the new one using the base backup you made before that. Then create a recovery.conf file and set the time of the parameter recovery target time within this file at the point you made the mistake, in this case 12:05 GMT. The recovery conf file is shown below. Place in mount server archive directory. So we have the restore command and the recovery target time. When Postgres starts up, it enters into pitter mode if there is a recovery.conf and a backup label in the database cluster. Pitter process is almost the same as the normal recovery process described in Chapter 9. The only differences between them are the following 2 points. 1. Where are wall segments / archive logs read from? Normal recovery mode. From the pgxlog subdirectory, or pgwall in version 10 or later, under the base directory. In pitter mode, from an archival directory set in the configuration parameter archive command. And point 2, where is the checkpoint location read from? In normal recovery mode, from a PG control file. In pitter mode, from a backup label file. The outline of pitter process is described as follows. 1. In order to find the redo point, Postgres reads the value of checkpoint location from the backup label file with the internal function read backup label. 2. Postgres reads some values of parameters from the recovery.conf, in this example, restore command and recovery target time. 3. Postgres starts replaying wall data from the redo point, which can be easily obtained from the value of checkpoint location. The wall data are read from archive logs, which are copied from the archival area to a temporary area by executing the command written in the parameter restore command. The copied log files in this temporary area are removed after using. In this example, Postgres reads and replays wall data from the redo point to the one before the timestamp 2019-1-29-1205 because the parameter recovery target time is set to this timestamp. If a recovery target is not set to, in the recovery.conf, Postgres will replay until the end of archiving logs. 4. When the recovery process completes, a timeline history file, such as 000000002.history, is created in the pgxlog subdirectory, or pgwall in 10 or later. If the archiving log feature is enabled, the same named file is also created in the archival directory. The contents and role of this file are described in the following sections. The records of commit and abort actions contain the timestamp at which each action is done. Xlog data portion of both actions are defined in XL exact commit and XL exact abort, respectively. Therefore, if a target time is set to the parameter recovery target time, Postgres may select whether to continue recovery or not. Whenever it replays Xlog record of either a commit or abort action. When Xlog record of each action is replayed, Postgres compares the target time of each timestamp written in the record, and if the timestamp exceeds the target time, pitter process will be finished. Note: the function read backup label is defined in source backend access transam xlog.c, and the structure xl exact commit and xl exact abort are defined in source include access exact.h. Note: why can we use common archiving tools to make a base backup? Recovery process is a process to make a database cluster in a consistent state, though the cluster is inconsistent. As PITR is based on the recovery process, it can recover the database cluster even if a base backup is a bunch of inconsistent files. This is the reason why we can use common archiving tools without a file system snapshot capability or a special tool. (10.3) Timeline ID and timeline history file. Timeline in Postgres is used to distinguish between the original database cluster and the recovered ones, and is a central concept of PITR. In this section, two things associated with the timeline are described: timeline ID and timeline history files. 10.3.1 Timeline ID. Each timeline is given a corresponding timeline ID, a 4-byte unsigned integer starting at 1. An individual timeline ID is assigned to each database cluster. The timeline ID of original database cluster created by the initdb utility is 1. Whenever database cluster recovers, timeline ID will be increased by 1. For example, in the example of the previous section, the timeline ID of the cluster recovered from the original one is 2. Figure 10.3 illustrates the PITR process from the viewpoint of the timeline ID. First, we remove our current database cluster and restore the base backup made in the past in order to go back to the starting point of the recovery, and such situation is represented in the red arrow curve in the figure. Next, we start the Postgres server, which replays wall data in the archive logs from the redo point created by the pg start backup until the recovery target by tracing along the initial timeline ID 1. And such a situation is represented in the blue arrow line in the figure. Then, a new timeline ID 2 is assigned to the recovered database cluster, and Postgres runs on the new timeline. As briefly mentioned in Chapter 9, the first 8 digits of wall segment file is equal to the timeline ID of the database cluster created for each segment. When the timeline ID is changed, the wall segment file will also be changed. Focusing on wall segment files, the recovery process will be described again. Suppose that we recovered the database cluster using 2 archive logs, 9 and 10. The newly recovered database cluster is assigned the timeline ID 2. The Postgres creates the wall segment from 0000002. The first bit is that timeline ID. Figure 10.4 shows this situation. So this 8-bit is incremented because it's the timeline ID. 10.3.2 Timeline history file. When a PITR process completes, a timeline history file with names like bunch of zeros 2.history is created under the archival directory and the pgxlog subdirectory, or pgwall in version 10 or above. This file records which timeline it branched off from and when. The naming rule of this file is shown in the following: 8-digit new timeline ID.history. A timeline history file contains at least one line, and each line is composed of the following three items: the timeline ID of the archive logs used to recover, the LSN location where the wall segment switches happen, reason, human readable explanation of why the timeline was changed. Here's an example. So if we cat out home Postgres archive logs, timeline ID.history, we see a single line, which is 1, which means that the base backup whose timeline ID is 1, the database cluster ID 2, and is recovered just before this time by replaying archive logs until this. In this way, each timeline history file tells us a complete history of the individual recovered database cluster. Moreover, it is also used to pitter process itself. The details explained in the next section. Note: the timeline history file format is changed in version 9.3. Formats of versions 9.3 or later and earlier are both shown now in detail. So up until version 9.2, we had timeline ID, wall segment, and reason, and now we see timeline ID, LSN, and reason. 10.4. Point-in-time recovery with timeline history file. The timeline history file plays an important role in the second and subsequent pitter processes. By trying the second time recovery, we will explore how it is used. Again, suppose you made a mistake at 12:15 in the recovered database cluster whose timeline ID is 2. In this case, to recover the database cluster, you should create a new recovery.conf shown below. So we have the restore command and the target time, which is now 12:15, and then we have the same restore command, but the recovery target timeline now is 2. The parameter recovery target time sets the time you made the new mistake, and the recovery target timeline is set at 2 in order to recover along its timeline. Restart the Postgres server and enter pitter mode to recover the database at the target time along the timeline ID 2. See figure 10.5. 1. Postgres reads the value of the checkpoint location from the backup label file. 2. Some values of the parameters are read from the recovery conf. In this example, restore command, restore target time, and recovery target timeline. Then 3. Postgres reads the timeline history file, bunch of zeros 2.history, which is corresponding to the value of the parameter recovery target timeline. 4. Postgres does replaying of the wall data by the following steps. 1. From the redo point to the LSN 0/A000198, which is written in the bunch of zeros 2.history file, Postgres reads and replays wall data of appropriate archive logs whose timeline ID is 1. Then 2, from the one after LSN 0/A000198 to the one before the timestamp 2019 1/29/12/15, Postgres reads and replays wall data of appropriate archive logs whose timeline ID is 2. 5. When the recovery process completes, the current timeline ID will advance it to 3, and the new timeline history file named bunchofzeros3.history is created in the pgxlog or pgwall subdirectory and the archival directory. When you do pitter more than once, you should explicitly set a timeline ID for using the appropriate timeline history file. In this way, timeline history files are not only history logs of database cluster, but also the recovery instruction documents for pitter process. Okay, be right back with the last chapter.